Howdy, calculus folks. What we're going to talk about in this lesson is a subject called limits at infinity. Okay. Now, the idea of limits at infinity is actually a completely separate subject of limits than what you have been learning in limits. See, the limits that you have been learning up to this point have been something like the limit as x approaches a finite value, like the limit as x approaches 3 of, let's say, x squared minus 8x minus 15 over x minus 3. And so to solve these, you would, plug 3 in. You'd solve for the numerator and the denominator. In this particular case, we would get 0 over 0, which would require us to use algebra and factoring or something like that. This would become x minus 3 times x. Was that a minus? That was supposed to be a plus 15. Sorry about that. Plus 15. X minus 3 and x minus 5. And so we would cancel the x minus 3's and then plug the 3 in. 3 minus 5 would be negative 2, and we'd get an answer. Okay, sorry about the mistake, but so here's the thing. This has a finite answer because on a graph, whatever this graph is, it probably looks something like this, and it has a hole at 3 somewhere. There it is. 3 is probably right about here. Okay. And so at x equals 3, the height of that hole is negative 2, and that's why the limit approaching from the left and approaching from the right is equal to negative 2. But what we're going to start talking about today are limits at infinity. And limits at infinity go like this. They'll say something like, what is the limit as x approaches infinity? Now there's two main differences, well, probably more than two main differences, but there's two very clear differences when dealing with a limit at infinity than doing a limit at a finite value. Limits at, the first one is what I just said, is that infinity itself is not a finite value. So you are not actually finding the height of a function as x is approaching an actual value. Okay, so that's the first difference. The other difference is that infinity does not have two sides. You can't come from the left side of infinity and from the right side of infinity and then approach a single value. In order to approach infinity, you have to just keep moving and keep moving infinitely because you're going to infinity. Okay, so this is a completely different idea than what we have been doing in limits. Okay, and there's two ways that you can approach limits at infinity as a student. You can approach limits at infinity as, wow, this is an amazing idea. I really want to understand in depth what it means. And then you can say, well, I just want to know how to be able to get the answer. And most videos that are out there, as this one will probably be, are really just about how do you find the answer to a limit at infinity. But if you want to understand the concept of what a limit at infinity is, you have to understand that limits at infinity are basically trying to answer the question, is there a horizontal asymptote? Is there a horizontal asymptote? And what is the horizontal asymptote? Meaning, what y value horizontal asymptote? What is the horizontal asymptote? Meaning, what y value is a graph approaching as it becomes flatter and flatter and flatter? And that's what's being implied here, is that the graph of the function is becoming flatter and flatter and flatter and flatter and flatter. And here's a visual, a graphical picture of what an asymptote would look like. A graph might do this. It might get closer to 0 and closer to 0 and closer to 0 and never actually touch 0. Now, it doesn't matter. It's okay for the graph to touch 0 and it can still have a horizontal asymptote at 0. A lot of people think that the definition of a horizontal asymptote means that the graph never actually touches that value. That's not the definition. The definition is at infinity, does the graph approach that value more and more closely, okay? And so, and what I mean by it can touch 0 is a lot of times what a horizontal asymptote will do is it'll actually touch 0 over here. Look, it's crossing over 0 right there, but that's not the important thing. The important thing isn't what the graph is doing locally, it's about what is the graph doing at the end. And there is no end, really. It keeps going on to infinity. But as the graph continues to infinity, is it getting closer and closer to a single y value? That's what the question of a limit at infinity is answering. Is there a horizontal asymptote? And if so, what is the horizontal asymptote? Generally, these questions fall into three main answers. Two of them have a horizontal asymptote with an answer, and the third one has no answer or no limit, okay, or there is no finite answer. When the answer is no limit, that means there is no horizontal asymptote, okay? So that's pretty much most of the conceptual understanding that I'm going to give you in this video. Now we're going to move on to, hey, Mr. Ryan, how do I answer these questions, okay? All right, well, this video is going to be a little bit different than the other videos that you have seen on this, probably because I am going to show you how to analytically determine what the limit at infinity is. By the end of the video, I will give you the little tricks. I will give you the tips and tricks on here's what you look for and this is how you answer the question. Okay? But I'm going to show you why those tricks work. And it all starts with being able to answer this question. What is the limit? Well, there's really two questions we have to be able to answer. Actually, three. If we can answer these three limits, then we can answer the three different types of questions. What is the limit as x approaches infinity of 1 over x? This is probably one of the most important limits at infinity. Okay, and we'll talk about that. Well, let's just go through this one right now. Okay, so here's the idea. When we say as x approaches infinity, what we mean is as x is becoming larger and larger and larger. And when we say larger and larger, we don't mean like 10, 11, and 12. We mean like a billion, a trillion, a Google. I mean just these immensely large numbers, like a 9 with 500 million nines after it, okay, and a whole mess of commas in there as well. These numbers are larger than anything that you can ever possibly imagine. So when I say x is becoming a large number, I mean way bigger than a number that you have ever thought of in your life, okay? But so that you want to, if you want to be able to conceptualize, let's just think in billions. Let's say that as x approaches infinity, we're talking about numbers past 9 or 10 billion or 100 billion or a trillion, much, much larger than the U.S. national debt, these numbers, okay? All right, so in order to get an idea of what's going to happen, what the answer to this is going to be, now, we cannot, I mean, we can, but we can't. We can't really plug infinity in here and then determine what is 1 divided by infinity, because you can't divide 1 by infinity. So we can get an idea of what the answer would be if we plug in really big numbers, okay? So remember, limits are as you are approaching, right? So why don't we put in numbers like, let's start with 10, okay? I know that's not, I said it wasn't a big number, but let's say it's 10. So we'll plug a 10 in. Then we'll plug in, let's say, 1,000, okay? 1 over 1,000. Then let's plug in 1,000,000. Then let's do 1 over 1,000,000. Whoops, there we go. And let's plug these numbers into a calculator and find out what their values are. Okay, so 1 divided by 10, of course, is 0.1, 0.1, okay? Well, okay, so now as we get closer to infinity, now it's 1 divided by 1,000. 1,000 is closer to infinity than 10 is. So we're going to do 1 divided by 1,000. And we get 0.001, so 0.001. Let's do 1 divided by 1 million. And we get 0.000001. So the question now is, what does it appear as our denominator here, as our x is approaching infinity, what is our output value? What is 1 over x approaching? What's the answer approaching? What does it look like to you? Well, 0.1, then 0.001, 0.000001. I mean, basically all we're going to do is keep putting zeros in here. Eventually we're going to have 0.000000000000000000000. It's just going to keep going, right? And then eventually at the end there's going to be a 1. Okay? This number, we're getting closer and closer to 0. That's right. That's because you should already understand that when the denominator gets larger and larger and the numerator is not changing at all, then that graph, as the inputs get larger, as this gets larger and larger, your answer gets closer and closer to 0. And so, and if you were to graph this, what you would see is that the graph of 1 over x does, as it gets larger and larger, it gets closer and closer and closer to the x-axis, which is 0. And therefore, the first thing you must understand, absolute rule, is that the limit as x approaches infinity of 1 over x is 0. Now this can be extended just a little bit further. Actually, it can be extended a lot further, but I just want to clarify something. What if we were to identify the limit as x approaches negative infinity of 1 over x? Well, it's the same thing. If we were to put in negative 10 or negative 100 or negative 1,000 or negative 1,000,000, all the answers would be the same except that they would be negative 0.1, negative 0.01, negative 0.00000000001. Okay, here the numbers are getting larger, but they're still approaching 0 from the bottom side. So going backwards, the values, if this is the graph of 1 over x, it does this. And the values are getting closer and closer and closer to the x-axis, which is 0. And so, even if we go from the backwards direction, our answer is 0. So, we're dealing mostly with rational functions that have polynomial numerators and denominators, and when that happens, the answer at infinity or negative infinity is pretty much going to be the same answer, okay? Pretty much. So if you can understand that the limit as x approaches infinity or negative infinity of 1 over x is 0, that's going to help you to answer lots more of these questions. All right, the second limit that you have to know kind of by heart is you have to know what is the limit as x approaches infinity of, let's say, 6 over 13. Okay? Now, I want to remind you about the properties of limits. And one of the properties of limits is the limit of as x approaches some value of a constant. Okay, so like, do you remember what is the limit as x approaches 9 of 17? And the answer is 17. That's because the function is a constant function, and therefore it doesn't matter what the x value is, the answer is always going to be 17. So this one now becomes very easy. 6 over 13, there's no variable in here. It's a constant, and therefore the limit as x approaches infinity of 6 over 13 is 6 over 13. That's right. This is a horizontal line, this 6 over 13. And that horizontal line is at 6 over 13 going all the way to infinity and all the way backwards to negative infinity. It's a horizontal line. It's not changing. So the limit as x approaches negative infinity of 6 over 13 is also 6 over 13. So now that's our second important limit that we have to understand. Not necessarily 6 over 13, but the idea of a constant, that the answer is going to be a constant. Now, I need to go back just for a second. I forgot to talk about something. Remember we said, what is the limit as x approaches infinity of 1 over x, right? And what's the answer to this? 0, right? Okay. Well, what if it was the limit as x approaches infinity of 1 over x squared, or 1 over x to the third, or 1 over x to the fourth, or x to the fifth, whatever? It doesn't matter. The answer is still 0. If you have no variable up here, if you have a constant in the numerator, even if this was 5 over x squared, it would still be 0. Anytime you have a constant in the numerator and a variable in the denominator, and that variable is approaching infinity, the answer is 0 every single time. Okay? All right, last one we want to look at is, I'll do a few of them. What is the limit as x approaches infinity of x? Or what is the limit as x approaches infinity of x squared? Or the limit as x approaches infinity of x to the third power? Well, these all have the same answer. Here's the idea. When x is 1,000,000, well, then the limit is 1,000,000. When x is 5 billion, then the limit is 5 billion. Which means that whatever we put here, we also put here. So really the answer is, since x is approaching infinity, well, what is the limit of infinity as x approaches infinity? Well, infinity doesn't have a limit, and therefore there is no limit. So what we would say, the limit as x approaches infinity of x is no limit, or does not exist. Say does not exist. Either way is fine, because there is no limit. Now, some teachers, some professors may want you to say which no limit. Is it positive infinity or negative infinity? Okay, well, if it's the limit as x approaches infinity, this number is getting larger and larger and larger, so it's positive infinity. Okay, but if we said the limit as x approaches infinity of negative x, well, then now all the numbers from here we put in here and they become negative, and now the answer is negative infinity. But I don't make my students do that. I'm fine with no limit. Does not exist. For me, infinity and negative infinity, you know, I mean, for the purposes of my class, I don't really care. Some classes, it's important. In my class, it's not important. All right, so now, what would the limit as x approaches infinity of x squared? Well, if x is, let's say we plug in 5 billion for x. Well, now it's going to be 5 billion squared. That's a huge number. It's much bigger than 5 billion, right? It's 5 billion times 5 billion, okay? It's 25 something million, okay? It's a much bigger number, but the fact remains that these numbers are getting larger and larger and larger and larger, and therefore, again, no limit. Okay, so it doesn't matter what the power is. If x is approaching infinity, and it's just a polynomial function where it's x to some power, where x, meaning x is not in the denominator. Remember, this is different than 1 over x to the third. The answer to that limit would be 0. This is just the limit of x to the third, and it's no limit. So if you can understand these three basic ideas, that the limit as x approaches infinity of 1 over x is 0, and the limit as x approaches infinity of some constant value, c, the answer is c, and that the limit as x approaches infinity of just x, or x squared, that the answer is no limit, then we can use these three concepts to answer any, well, not any polynomial, like any limit of a rational function with polynomial parts. Now, we'll get to non-polynomial parts in just a little bit, okay? But what we can now do is we can now answer questions like this. What is the limit as x approaches infinity of, let's say, 7x squared minus 4x plus 6 over 9x to the fourth power plus 2x squared plus 1. Let's say that we have this problem. And here's the rule. I'm going to write the rule down. Here's the rule. The way that one very useful and very well accepted technique for solving this limit is to take all of the pieces, that piece, that piece, that piece, that piece, that piece, that piece, all of the terms in the entire limit in numerator and denominator, and divide them by the variable of the highest power in the denominator. Okay, so divide all terms by the highest power variable in the denominator. So denominator's highest power. Okay? So in this case, what is the highest power of the denominator? Well, the variable is x. And in the denominator, the highest power is 4. So what we're going to do is we're going to divide everything by x to the 4th power. This, and this. Okay? And we're going to show you what happens when you do that. So here's what it's going to become. This is going to become the limit as x approaches infinity of, here we go, 7x squared over x to the 4th minus 4x over x to the 4th plus 6 over x to the 4th over 9x to the 4th over x to the 4th plus 2x squared over x to the 4th plus 1 over x to the 4th. Equals. And now what we have to do, now we're going to go through and we're going to algebraically deal with all of these individual terms. Because look at this. For example, here, these x to the 4th and the x to the 4th, those cancel. And now what we have is the limit as x approaches infinity of, here's what we're going to have. So this first term, we're canceling the x to the 4ths. So we're just going to have a 9 here. Plus, now here, do you see this? This has an x squared up top and an x to the 4th on the bottom. So that's going to turn into, that x squared is going to cancel, and this x to the 4th is going to become an x squared. So this is now going to be 2 over x squared plus 1 over x to the 4th. Okay? Now in the numerator, here we're going to cancel the x squared, and this x to the 4th is going to turn into x squared. So we're going to have 7 over x squared minus, and then we're going to cancel 1x and one of the x's down here, so that's going to become x to the 3rd, so 4 over x to the 3rd plus 6 over x to the 4th. And now, watch what's going to happen. Now we're going to go back to our properties of limits that we learned. And what we can now do is, this is a quotient. So what we can do is we can split it up into two separate limits. We can do the limit as x approaches infinity of the numerator, and then the limit as x approaches infinity of the denominator. Okay? As long as the limit as x approaches infinity of the denominator is not 0. And so we can find out if it will be by, watch this. Then we're going to take the property where the addition and subtraction property of limits, and we're going to do each one of these little individual pieces as a separate limit. So here's what we're going to do. Let's go ahead and figure this out. We're going to do the limit as x approaches infinity of 7 over x squared. Well, what does that equal? Well, anytime you have a constant over an x, that's like this one, constant over x. So what's the answer? It's 0. So it's going to be 0. So we're going to make a fraction here. How about, what's the limit as x approaches infinity of 4 over x to the 3rd? Also 0. So minus 0. And then what is the limit as x approaches infinity of 6 over x to the 4th? Again, it's of the form 1 over x. It's a constant over an x. So it's 0, so plus 0. Down here, what is the limit as x approaches infinity of 9? Well, that's kind of like this one here. That's the limit as x approaches infinity of a constant. And the answer is the constant. So the limit as x approaches infinity of 9 is 9. What is the limit as x approaches infinity of 2 over x squared? Well, that's kind of like this one up here again. It's 0. So we're going to put plus 0. And then what is the limit as x approaches infinity of 1 over x to the 4th? Again, it's like this one up here. So the answer is 0. So plus 0. So when we do all this, we get 0 minus 0, 0, plus 0, 0, over 9 plus 0 plus 0 is 9. And what is 0 over 9? It's 0. So the answer to this limit right here is 0. Okay? Analytically, algebraically, we figured it out. Now, this was kind of overkill for this kind of limit. But here's the thing, is that if you learn how to do limits this way, it'll prepare you for when you do more complicated limits at infinity that have more complicated pieces. Okay? So it's a good practice. It's something to remember. Let's do another one, shall we? Also, I want to point something out to you. You may have already seen a video like this, but the basic trick goes like this, is if you're doing a limit at infinity, if the power of the denominator is larger than the power of the numerator, then the limit at infinity is 0, and this meets that requirement. Okay, and there's other ways to look at that, but I'm not going to do that right now. All right, let's do another one. Let's just use this same problem but change it up a little bit, shall we? Let's just change some of the powers. Let's say that this was x to the 3rd power up here, and this was also x to the 3rd power down here. So let's say that we have the same highest power in the numerator and the denominator. Now, some of you already know what's about to happen, but I'm going to show you anyway. All right, we're going to do it the way that we just did it. What's the highest power of the denominator? X to the 3rd power. So we're going to divide each of the terms by x to the 3rd power. So we're going to have the limit. And by the way, it works at negative infinity also. The limit as x approaches infinity of, here's what we're going to do, 7x to the 3rd over x to the 3rd minus 4x divided by x to the 3rd plus 6 over x to the 3rd divided by 9x to the 3rd over x to the 3rd plus 2x squared over x to the 3rd plus 1 over x to the 3rd. We have divided all of the terms by x to the 3rd. And it is algebraically legal to do that. What we're basically doing is we're multiplying the top and the bottom times 1 over x to the 3rd over 1 over x to the 3rd. And 1 over x to the 3rd divided by 1 over x to the 3rd is equal to 1. So this is an appropriate manipulation. Okay? All right, so now, here, this x to the 3rd, that's going to cancel, and we're going to have a 7 on the top. Down here, the x to the 3rds are going to cancel, and we're going to have a 9. 4x over x to the 3rd, 1x is going to cancel, and we're going to have x squared. Okay, so we're going to have minus 4 over x squared. Down here, the x squared is going to cancel. 2 of the x's here are going to cancel. We're just going to have 2 over x plus 2 over x. Here we have plus 6 over x to the 3rd. Down here we have plus 1 over x to the 3rd. And if we're doing the limit as x approaches infinity of this, here's what we have. We're going to do the limit as x approaches infinity of each individual piece in the numerator and then each individual piece in the denominator. And we're allowed to do that because of the properties of limits. Now, we can only get away with it if the denominator does not equal 0. Okay? So now, the limit as x approaches infinity of 7 is 7. The limit as x approaches infinity of 4 over x squared is kind of like this one. It's 0. So minus 0. The limit as x approaches infinity of 6 over x cubed is 0. So that's plus 0 over. The limit as x approaches infinity of 9 is just 9. The limit as x approaches infinity of 2 over x, that's 0. So plus 0. And then the limit as x approaches infinity of 1 over x to the third is also 0. And therefore, our answer is 7 minus 0 plus 0 is 7. And 9 plus 0 plus 0 is 9. And so our answer is 7 over 9. Okay? Now, the answer is 7 over 9. You may have seen the shortcut trick, which is fine, it works, that when you're doing a limit at infinity, if the power of the numerator is the same as the highest power, the degree, if the degree of the numerator is equal to the degree of the denominator, then your answer, your final answer really is just the ratio of the lead coefficients, 7 over 9. Oops, I put a 4 there. That was a huge mistake. Which, that is the right answer, 7 over 9, right? So 7 over 9, okay? All right, let's try the third kind of limit at infinity. All right, so here's our third kind here. And now you'll notice that in this particular case, the power of the numerator is larger than the power of the denominator. That's our third kind. And you may already know the trick for coming up with this answer, okay? But let's go ahead and work through it with our normal rule, which is divide by the highest power of the denominator. The highest power of the denominator is 4. So we're going to divide all of these terms by x to the 4th power. So we're going to have the limit as x approaches infinity of 7x to the 5th over x to the 4th minus 2x over x to the 4th plus 1 over x to the 4th. In the denominator, 9x to the 4th over x to the 4th plus x squared over x to the 4th minus 3 over x to the 4th. Now, let's see what this becomes. We've got the limit as x approaches infinity. In the top here, we're going to cancel the x to the 4th on the bottom and 4 of the x's on the top, leaving us with 7x. Minus, here we're going to cancel the x on the top and 1 of the x's on the bottom, so that'll be x to the 3rd. So we'll have 2 over x to the 3rd. And then plus, we can't cancel anything here. We'll just have 1 over x to the 4th. Over 9x to the 4th divided by x to the 4th is just 9. And then x squared divided by x to the 4th, that cancels the x squared, leaving a 1. And it gets rid of 2 of the x's down here, leaving x squared. So we have plus 1 over x squared. And then this, we can't cancel anything. We just have minus 3 over x to the 4th power, right? Okay. So now, here's what we're going to do. We're going to do the individual limits of each one of these by the properties of limits. Okay, well, what is the limit as x approaches infinity of 7x? That's a problem because the answer is no limit. Well, that's going to stop us in our tracks here because I got to put a number over here and I can't put a number because there's no limit for this. Okay, so here's what I'm going to do instead. I'm actually going to do this one last. What I can do is I can work backwards. I can come over here and I can say, what is the limit as x approaches infinity of 1 over x to the 4th? Well, that's 0 because it's kind of like 1 over x. So I can basically put a 0 there. And what is the limit as x approaches infinity of 2 over x to the 3rd? Well, that's the same thing as 1 over x. So I'm going to put a 0 there. So what is 7x minus 0 plus 0? Well, it's just 7x. So I'm going to put a 7x here. I'm going to carry over the limit as x approaches infinity, right? Now here, what is the limit as x approaches infinity of 3 over x to the 4th? Well, that's 0 again. It's just like this one up here, 1 over x. So that's 0. Anytime you have x's in the bottom and no x's in the top, the limit at infinity is 0. So this is going to become 0. There we go. And so now, the limit as x approaches infinity of 9 is 9. So we have 9 plus 0 minus 0 is just 9. So here's what we really have now. We just boiled this down to what is the limit as x approaches infinity of 7x over 9. And here's the thing. This can also be written as 7 over 9x. But the bottom line is this. Well, that's not the answer. But the bottom line is this function, if you were to plug bigger and bigger numbers in, because this x is not in the denominator, it's basically like this one right here. These numbers are just going to get larger and larger and larger and larger and larger. They're not going to get closer and closer and closer to any number. And because the power, this x is in the numerator, because this number is going to get bigger and bigger and bigger, there is no limit. And that leads us to the third shortcut trick, or just the thing you memorize. And the idea is, that third thing is this, is that when the power of the numerator is larger than the power of the denominator, then the limit at infinity is no limit. There is no limit. And that's what you answer, no limit. So there's only really 3 possible answers. And you're looking at them pretty much right here. When the power of the denominator is larger, the limit at infinity is 0. When the power of the numerator and denominator are the same, the limit at infinity is going to be a constant that is not 0. It's going to be the ratio of the lead coefficients of the numerator and the denominator. And then if the power of the numerator is higher than the power of the denominator, then the answer is no limit. That means there is no limit. There is no horizontal asymptote. It goes up forever or it goes down forever. Okay? All right. Let's do a couple of examples. All right, how about this one? We've got the limit as x approaches negative infinity of 4x squared minus 5 over 3x squared plus 7. The power of the numerator is the same as the power of the denominator, and so basically the answer is going to be the ratio of the lead coefficients, 4 over 3. So the answer to this, very simply, 4 over 3. All right, let's look at this one. We've got the limit as x approaches infinity of 7 minus x cubed over x squared plus 1. Now, it does not matter what order these terms are in. What matters is what is the highest power in the numerator and what is the highest power in the denominator. Well, the highest power of the numerator is 3. The highest power of the denominator is 2. Since the power of the numerator is higher than the power of the denominator, there is no limit. No limit. Let's try a third one. All right, let's look at this one. We've got the limit as x approaches infinity of 4x minus 9x squared over 1 minus x to the 5th power. Now again, it doesn't matter what order they're in. It just matters what's the highest power. The highest power in the numerator is 2. The highest power in the denominator is 5. And because the highest power in the denominator is larger than the highest power in the numerator, the answer is going to be 0. And that is the limit at infinity. Okay? Now I'm going to show you one more special kind of limit at infinity, and then that's going to be everything. Okay, anytime you're dealing with a limit at infinity that involves an exponential function, you have to remember that exponential functions behave differently at positive infinity than they behave at negative infinity. Okay? So if you have an exponential function like 3 to the x power, or 4 to the x power, or 2 to the x power, or 1.5 to the x power, or e to the x power, anything, any value, any constant value to a variable power, then that is an exponential function. Here's what you need to understand is that whenever you raise a value to a positive power, the numbers get larger and larger and larger. That's assuming this number is larger than 1. Anytime you take a number larger than 1 and raise it to a positive power, that number will get larger and larger and larger and larger and larger and way larger. Exponentially larger because it's an exponential function. On the other hand, exponents that are negative, if you take a number larger than 1 and you raise that number to a power that is negative, then the value is actually going to get smaller and smaller and smaller and smaller and smaller and smaller and smaller, but it's never actually going to be 0. It's going to get smaller and it's going to get closer to 0. In fact, exponential functions at negative infinity have a horizontal asymptote. They approach 0. But exponential functions at positive infinity, they go up, 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 and they have no limit. So we have to understand this. When you see an exponential function, even as a part of a function in a limit, you have to think to yourself, well, is the exponential function, is the exponent going to positive infinity, or is the exponent going to negative infinity? If the exponent is going to positive infinity, then you can assume that that number is getting larger and larger and larger, and it has no limit. It's just a gigantic number. But if your exponent is going to negative infinity, then you can just assume that that piece, that exponential piece, is basically equal to 0. And I want you to remember that as I do a couple examples in just a minute. Okay, so let's look at this one. We've got the limit as x approaches infinity of 8 to the x power minus 12 over 3 plus 8 to the x power. Now you're going to need to use a little bit of your imagination to be able to understand what I'm about to explain. But in order to solve this, the first thing we want to ask ourselves is this, is we have an exponential term. And usually when you see these, you'll see the same base in the numerator and the denominator. Okay, it won't really, well, it's a little more complicated when it's not the same number. Not that complicated, but it's a little more complicated. So here's the deal. This is x approaching positive infinity. So that's positive infinity, and that's positive infinity. So this is getting excessively large, this 8 to the x power. This 8 to the x power is getting excessively large. And here's what I want you to understand is, see this minus 12 and this 3 plus? Here's what I want you to know is that compared to how big this 8 to the x power is, these numbers are irrelevant. They may as well be 0. Here's why. Let's say that you have $1 billion in the bank. And then you're walking along the sidewalk and you see a nickel. Now you can pick up that nickel and keep it for good luck, and you can do whatever you want with that nickel. But has that nickel significantly impacted your wealth? You have $1 billion in the bank and you just found a nickel. So now you have $1 billion and 5 cents. Is $1 billion and 5 cents significantly larger than $1 billion? And most people would answer, no, it's not. In fact, most people who have $1 billion and 5 cents would basically just say that they have $1 billion. And so when we're dealing with exponential functions at positive infinity, the constants that go along with them are irrelevant, and we can ignore them. So this is basically the same thing as the limit as x approaches infinity of 8 to the x power over minus 0, which is 8 to the x power, over 0 plus 8 to the x power, which is just 8 to the x power. And what is 8 to the x power divided by 8 to the x power? It's 1. And so that's what the answer to this limit would be. It would be 1. On the other hand, what if we had the limit as x approaches infinity, or excuse me, as x approaches negative infinity of the same problem? 8 to the x power minus 12 over 3 plus 8 to the x power. Now what would it be? Well, this significantly changes the problem. Now that it's the limit as x approaches negative infinity, this is 8 to the negative infinity power. And what did I tell you about exponential expressions that have exponents that go to negative infinity? They are essentially 0. And so this 8 to the negative infinity power is essentially 0. This 8 to the negative infinity down here is essentially 0. So what we're looking at here is 0 minus 12, which is negative 12 over, this is 3 plus 0, which is 3. And what is negative 12 divided by 3? Negative 4. And that would be your answer to this limit at negative infinity. Okay? And so these are special cases of limits at infinity of rational functions that include exponential elements to them. Okay? And so I want you to know these as well. Well, that's all I have for you. There's a worksheet that goes along with it. Make sure you work through all these limits. If you have any questions, let me know, and I will see you in class, and good luck.